Hello everyone, this is Kalpana here. In this video, we are going to solve the given differential equation. So let's get going. Problem: solve x cube e power x minus 2my square into dx plus 2mxy into dy equals to 0. Solution: given differential equation x cube e power x minus 2my square into dx plus 2mxy into dy equals to 0. Right? Consider it as equation 1, which is in Mdx plus Ndy equals to 0 form, where by comparing these two equations we'll get m equals to x cube e power x minus 2my square and n equals to 2mxy. If partial derivative of m with respect to y is equals to partial derivative of n with respect to x, then we can call the given equation as an exact equation. Okay, so let's find partial derivatives. Firstly, we'll find partial derivative of m with respect to y, which is equals to dou y of for m x cube e power x minus 2m y square is equals to partial derivative of first term with respect to x minus partial derivative of second term with respect to y. Okay. Which is equals to, here we are doing partial derivative with respect to y. It does not involve any y. We'll treat x as constant here. Okay, since we are doing partial derivative with respect to y, so x is treated as constant. So partial derivative for constant with respect to y is 0 minus, write the constants outside the integral, 2m into partial derivative of function of y with respect to y equals to minus 2m into partial derivative of y square with respect to y is 2y, which is equals to minus 4my, right? So we have partial derivative of m with respect to y is equals to minus 4my. Now let's find the partial derivative of n with respect to x. This is your m and this is your n. Partial derivative of n with respect to x equals to dou by dou x of 2m xy. Write the constants outside the integral. Since we are doing partial derivative with respect to x, we'll treat the remaining as constant. Okay. So, constant into partial derivative of x with respect to x equals to 2my into partial derivative of x with respect to x is 1, which is equals to 2my. So therefore partial derivative of n with respect to x equals to 2my. Right? From this we can say that partial derivatives are not equal. Therefore partial derivative of m with respect to y is not equals to partial derivative of n with respect to x. From this we can say that equation 1 is non-exact. Okay. Now we need to find a suitable integrating factor to reduce the given equation to an exact equation. Right. So the given equation is non-exact and it is non-homogeneous if dy by dx is not equals to some function of xy, that is for k. If you can write the given equation as dy by dx equals to function of xy, if this function of xy for f of kx equals to ky equals to f of xy, then we can say that this function is a homogeneous function. If this does not happen, then we call the differential equation involving non-homogeneous function as non-homogeneous differential equation. If f of kx, ky equals to f of xy, then the function in the differential equation, then this function in the differential equation is called homogeneous function, and the differential equation involving homogeneous function is called homogeneous differential equation. If this does not happen, then we call this differential equation as non-homogeneous. Fine. Now, and also the given equation is not in the form of y into some function of xy into dx plus x into some function of xy into dy equals to 0. Right? Now, by looking at this, we can say that the difference of these two will be the term in my, right? And also in m you're having two terms, and in n you're having only one term involving m and y. So find 1 by n times partial derivative of m with respect to y minus partial derivative of n with respect to x. This is equals to 1 by, for n, 2mxy into partial derivative of m with respect to y is minus 4my minus partial derivative of n with respect to x is 2my, which is equals to minus 4my minus 2my is minus 6my by 2mxy, where y gets cancelled and m gets cancelled, right? So by looking at these three, we can say that you're having m and y common. So there's a chance of eliminating m, y by using this formula. Okay? And you'll get a function of x alone. Okay? See, it does not involve any other variable other than x. So we call it as function of x alone, and you can name it as some f of x. Now, our integrating factor is given by e power integral f of x into dx, which is equals to e power integral minus 3 by x into dx, which is equals to e power minus 3 into integral 1 by x dx equals to e power minus 3. Integral 1 by x dx is log mod x. Again, you can write this as e power minus 3 log x, which is equals to e power, since we know that m log n can be written as log n power m. Then you can write minus 3 log x as log x power minus 3. And also we know that e power log some function of x can be written as function of x. So here our function of x is x power minus 3, which is reciprocal of x cube. Okay. So this is a integrating factor. See, here we got function of x. So our integrating factor is e power integral f of x. What happens if we get some real constant instead of function of x? By using this formula, we can get either function of x alone or some real constant, say k. Okay, if we get real constant k, then our integrating factor will be e power integral k into dx. By looking at f of x, we write dx, right? We write dx, but how we can remember to write dx when we'll get k? Simply, here you're having 1 by n, right? N. So, we'll always do partial derivative of n with respect to x, right? So, write dx here. Okay, it will be easy to remember. If you have n, you'll write dx. If you have m here, you'll write dy. Fine. Now we are having integrating factor 1 by x cube. So by multiplying the integrating factor to the given equation can be reduced to an exact equation. Now we need to multiply the integrating factor to the given equation. 1 by x cube times the given equation gives an exact equation. Okay, then 1 by x cube times x cube into e power x minus 2m y square into dx plus 1 by x cube into 2mxy into dy equals to 0. Then x cube minus e power x into 1 by x cube is x cube e power x cube by x cube minus 2my square into 1 by x cube is 2my square by x cube into dx plus here you can write this as 2mxy by x cube into dy equals to 0. So x cube gets cancelled. Here we don't have any x in the numerator to cancel x, but here 2x gets cancelled. Then the reduced equation is e power x minus 2my square by x cube into dx plus if 1y gets cancelled, you'll get 2my by x square into dy equals to 0, which is in m1 dx plus n1 dy equals to 0 form, right? Where m1 equals to e power x minus, by comparing these two we'll get m1. Okay, so consider this equation as equation 2, the equation obtained by multiplying integrating factor. Okay, e power x minus 2my square by x cube and n1 equals to 2my by x square. So if the partial derivative of m1 with respect to y is equals to partial derivative of n1 with respect to x, then we can say that the reduced equation is an exact equation, that is an equation obtained from multiplying the given equation with integrating factor is an exact equation. Okay, so let's find partial derivatives of m1 and n1. Firstly, we'll find the partial derivative of m1 with respect to y. Dou by dou y for m1 e power x minus 2my square by x cube. Since we are doing partial derivative with respect to y, So remaining variables will be treated as constant, or you can write this as dou by dou y of first term e power x minus dou by dou y of second term 2my square by x cube is equals to partial derivative of a constant is 0 minus, write the constants 2m by x cube outside the derivative, then you'll get 2m x cube into partial derivative of y square is equals to minus 2m by x cube into partial derivative of y square with respect to y is 2y, which is equals to minus 2 2s are 4 m y by x cube. Therefore, partial derivative of m1 with respect to y equals to minus 4my by x cube. Now we'll find the partial derivative of n1 with respect to x. Partial derivative of n1 with respect to x equals to dou by dou x of, for n1, 2my by x square is equals to, here 2my is constant, so you can write this as constant into partial derivative of 1 by x square. Since we are doing partial derivative with respect to x, so we'll treat the remaining variables as constant. Here y is a variable, m is a constant, 2 is a constant, okay? So since we are doing partial derivative with respect to x, so we'll treat this variable y as constant. So you can write this as partial derivative of reciprocal of x square can be written as x power minus 2, which is equals to 2my into derivative of x power minus 2 with respect to x is minus 2 into x power minus 2 minus 1, which is equals to 2 into minus 2 is minus 4 my into, or better you can write this as 2mxy into minus 2 into x power minus 3, which is equals to 2 into minus 2 into my into x power minus 3. We'll make it simple, okay? Is equals to 2my into minus 2 into, since we know that x power minus n can be written as reciprocal of x power n, then you can write x power minus 3 as 1 by x cube. Now this equals to 2 into minus 2 into my into 1 by x cube, which is equals to 2 into minus 2 is minus 4 my by x cube. Therefore, partial derivative of n1 with respect to x is minus 4my by x cube. So from this we can say that therefore partial derivative of m1 with respect to y equals to partial derivative of n1 with respect to x equals to minus 4my by x cube. Since the partial derivatives are equal, so we can say that equation 2, which is obtained by multiplying integrating factor to the given equation, is exact equation. Therefore, equation 2 is exact. Okay. Now, we'll find the general solution to the given equation. So, the general solution obtained by this exact equation will be the general solution to this equation. We know that the general solution of an exact equation m1 dx plus n1 dy equals to 0 is given by integral over x m1 dx plus integral of terms of n1 free from x into dy equals to c. Okay. So now using this formula, we'll find the general solution to the given equation. Since the exact equation, the reduced equation is exact and which is in the form of m1 dx plus n1 dy equals to 0. So we wrote general solution in m1 and n1. Okay. The general solution to the given equation is integral over x m1 dx plus integral of terms of n1 free from x into dy equals to c, right? So firstly we'll evaluate the first integral. Integral over x m1 dx. Integral over x in the sense here y is treated as constant. For this integral we'll treat y as constant. This is equals to integral over x e power x minus 2m y square by x cube into dx. Okay, y is treated as constant here. Is equals to integral e power x dx minus integral 2m y square by x cube into dx equals to integral e power x dx minus, write the constants outside the integral, you'll get 2m y square into integral 1 by x cube into dx. Is equals to integral e power x dx minus 2m y square into, since we know that 1 by x power n equals to x power minus n, then you can write 1 by x cube as x power minus 3 into dx. Since we know that integral e power x dx equals to e power x plus c, and integral x power n dx equals to x power n plus 1 by n plus 1 plus integral constant c for n not equals to minus 1. So we have n equals to minus 3 which is not equals to minus 1. So we can apply this formula to this, and there's 2 integral e power x dx. This becomes, so we don't write plus c, integral constant plus c for every integral. Okay, we'll finally write once in the general solution. So this becomes e power x minus 2m y square into x power minus 3 plus 1 by minus 3 plus 1 equals to e power x minus 2m y square into x power minus 3 plus 1 is minus 2 by minus 2. Okay. Then this becomes e power x minus 2m y square into, we can write 1 by minus 2 as minus 1 by 2 into x power minus 2. We'll just split this as 1 by minus 2. Better you can split this as 1 by minus 2 into x power minus 2. Since x power minus n equals to 1 by x power n, then this becomes e power x minus 2my square into, you can write 1 by minus 2 as minus 1 by 2 into write x power minus 2 as 1 by x square. This is equals to e power x minus into minus plus 2 gets cancelled and you'll get my square by x square. Sorry, not x cube, x square. Therefore, integral over x m1 dx is e power x plus my square by x square. Now, we'll find the second integral. Integral of terms of n1 free from x into dy. See, you are having n equals to 2my by x square, which is not free from x because it has x square, right? So the variable x exists in n. So terms of n free from x is 0 into dy, which is equals to 0. Now the general solution becomes the general solution of 1 otherwise is result obtained from the first integral e power x plus my square by x square plus result obtained from the second integral 0 equals to c. We can write this as, I'll write the same thing firstly. So now take the LCM of first two terms of LHS. X square is your LCM. In the numerator you'll get e power x into x square e power x plus my square equals to c. Now take this x square to RHS, you'll get x square e power x plus my square equals to c into x square. Now bring this c x square to LHS, you'll get x square e power x plus my square minus cx square equals to 0. Write the x square terms first and then the remaining term. Now you can notice x square existing in the first two terms. So we'll take x square common from these two terms and we'll get x square times e power x minus c plus my square equals to 0, which is a required solution. So we have seen a problem from differential equation in this video. Hope you'll understand. We'll see you in the next video. Until then, bye bye.